The rail yards of post-war Britain were places of waiting. Steel rested on steel. Diesel fumes drifted without urgency. In coastal shipyards, hulls sat motionless at the waterline, their outlines fixed against a grey horizon. The war had ended, but its tempo lingered in the infrastructure it left behind. Across the country, systems built for conflict were being repurposed for continuity. Rail lines stretched through industrial towns and open countryside, linking cities that no longer moved at wartime speed. Naval bases remained active, but much of their activity was procedural rather than urgent. Maintenance replaced deployment. Inspection replaced alertness. Within these environments, machinery was judged less by spectacle than by endurance. Engines were expected to start reliably, run continuously, and accept long hours without complaint. Noise was tolerated. Complexity was not. The prevailing instinct favored designs that could be understood quickly and repaired without delay. Yet beneath this surface calm, a different current existed. British industry faced pressure to modernize with fewer resources. Fuel efficiency mattered. Power-to-weight ratios mattered. Space aboard ships and within locomotives mattered. Solutions were being sought quietly, without public attention. It was in this restrained, methodical atmosphere that an unconventional engine began to move from drawing offices into physical space. Its arrival was not dramatic. There were no announcements. Only the gradual presence of something unfamiliar, placed among familiar surroundings, and left to prove whether it could endure. Britain emerged from the Second World War with intact institutions but strained capacity. Industrial plants had worked continuously for years. Skilled labor was depleted. Materials were rationed. Fuel was costly, and imports were uncertain. The nation's engineering culture, long defined by incremental reliability, was being asked to deliver efficiency under constraint. Rail transport remained essential. Steam locomotives still dominated the network, but they were labor-intensive and increasingly expensive to maintain. Diesel traction offered advantages in range and staffing, yet early diesel engines struggled to match the power output required for mainline service without adding weight and bulk. Similar problems existed at sea. Naval vessels required compact engines capable of sustained high output, particularly for fast patrol boats and minesweepers operating in shallow or constrained waters. Within this context, engine manufacturers were encouraged to explore unconventional solutions. One of these firms was Napier Son, an established British company with experience in aero engines and marine propulsion. During the war, the firm had contributed to aircraft engine development, including high-output designs that prioritized power density over simplicity. After 1945, Napier's engineers faced a narrowing market for large aviation engines as jet propulsion accelerated. The company turned its attention toward diesel technology, where military and civil demand remained stable. The challenge was clear: produce an engine that delivered high power from a small footprint, consumed less fuel than steam or gasoline alternatives, and could operate continuously under load. Institutional support followed cautious evaluation. The Royal Navy and railway authorities did not seek novelty for its own sake. They sought performance within limits. Napier's proposals were reviewed not as experiments, but as potential answers to practical constraints. What followed was not a sudden leap, but a deliberate decision to pursue a design that departed from established convention. That decision set the conditions for an engine that would require constant attention, precise handling, and acceptance of complexity as a trade-off rather than a flaw. The engine Napier proposed did not resemble existing diesel designs. It did not follow the linear arrangement common to locomotives, nor the radial logic familiar from aircraft engines. Instead, its structure formed a closed triangle, with three banks of cylinders arranged at 120-degree angles. At each corner sat a crankshaft. Between them, pistons moved toward and away from each other without the use of cylinder heads. This configuration became known as the Napier Deltic, named for its triangular layout and delta-like geometry. Each cylinder contained two pistons, one entering from each end. As they approached one another, combustion occurred in the space between them. Exhaust and intake ports were uncovered by piston movement rather than valves, simplifying airflow while demanding precise timing. The advantages were measurable. Without cylinder heads, heat loss was reduced. The opposed piston design allowed for more complete combustion. The triangular arrangement permitted multiple crankshafts to share the load, enabling very high power output relative to the engine's overall size and weight. For naval vessels where space was limited and speed was critical, these characteristics were attractive. The costs were equally clear. The engine required exact synchronization between 3 crankshafts. Lubrication paths were complex. Access for maintenance was limited by the dense arrangement of components. Manufacturing tolerances had to be held tightly across dozens of moving parts. Any imbalance could propagate through the system. Napier's engineers were aware of these risks. Prototypes were built and tested extensively. Performance figures met expectations. The engine ran fast, produced high output, and consumed less fuel per unit of power than many alternatives. On paper and in controlled trials, the design justified its complexity. What could not be fully simulated was long-term operation under field conditions. The engine's success depended not only on design, but on disciplined upkeep and consistent operating standards. By committing to the Deltic's architecture, users were accepting a machine that would demand attention continuously, not occasionally. Once that commitment was made, reversal would be difficult. The triangle, once assembled, left little room for improvisation. The transition from prototype to service occurred gradually, but once begun, it narrowed options quickly. The first large institutional user to commit was the Royal Navy, whose post-war requirements emphasized speed, compactness, and operational endurance. Smaller vessels, fast patrol boats, minesweepers, and torpedo craft, were increasingly expected to operate independently, often at high output, and within confined machinery spaces. Conventional diesel engines capable of meeting these demands were either too large or too heavy. Gas turbines were not yet mature for sustained marine use. The Deltic engine, with its high power-to-weight ratio, offered a solution that aligned with emerging naval doctrine. Trials demonstrated that vessels equipped with Deltics could achieve and maintain speeds that were difficult to match with alternative propulsion systems. Once installed, the engines reshaped ship design. Engine rooms were laid out specifically around the triangular units. Cooling systems, exhaust routing, and access points were configured to suit their geometry. Training programs were adapted. Spare parts inventories were restructured. The decision to adopt the Deltic was no longer isolated to the engine itself, it propagated through the vessel as a system. A similar process unfolded in rail transport. British rail authorities faced pressure to modernize traction while reducing operating costs. Mainline diesel locomotives required sustained high output without the labor demands of steam. The Deltic's performance characteristics, proven at sea, appeared transferable to rail use. Once again, trials led to confidence, and confidence led to commitment. At this stage, the point of no return was not a single failure or crisis, but institutional momentum. Infrastructure was adapted. Personnel were trained. Maintenance depots were equipped with specialized tools. The engines were no longer experimental units that could be withdrawn quietly. They were embedded in operational fleets. From that moment forward, success depended on continuous conformity to the engine's demands. The Deltic could not be simplified without undermining its function. It could not be treated casually without consequence. What had been accepted as an engineering solution now became an operational condition. The machine had been chosen. The system around it would have to survive. Once the Deltic engines entered regular service, novelty disappeared quickly. What remained was routine. The engines were expected to start on schedule, reach operating speed without hesitation, and sustain high output for extended periods. Their performance advantages were real, but they existed only when the engines were treated exactly as intended. Daily operation began before ignition. Oil levels were checked across multiple systems, not a single sump. The Deltic used a distributed lubrication network feeding 3 crankshafts, gear trains, and auxiliary drives. Any imbalance in oil pressure could indicate developing failure. Filters were inspected frequently. Contamination, even in small amounts, carried risk. Starting procedures were formal and sequential. The engine did not tolerate shortcuts. Air start systems had to deliver sufficient pressure. Timing between crankshafts was monitored indirectly through vibration and sound. Experienced operators learned to identify irregularities by ear, distinguishing normal mechanical noise from early warning signs. This was not intuitive knowledge. It was acquired slowly, through repetition. Once running, the engine operated at high rotational speeds compared to conventional diesels. This contributed to its power density but increased wear. Heat management was constant. Cooling systems were heavily loaded, and temperature margins were narrow. Operators monitored gauges continuously, adjusting output to remain within limits rather than pursuing maximum performance. Maintenance schedules were strict and frequent. Components that might run for thousands of hours in simpler engines required inspection at shorter intervals. Bearings, seals, and gear meshes were checked methodically. Accessing internal components often required partial disassembly. The triangular layout restricted movement and visibility, increasing labor time. Crews adapted by developing routines that emphasized consistency. Tasks were logged carefully. Deviations were noted. Informal knowledge circulated among engineers, but it remained grounded in observation rather than assumption. The engine did not respond well to improvisation. Solutions that worked on other diesels were not always applicable. At sea, the operational environment added complexity. Salt air accelerated corrosion. Vessel motion affected lubrication distribution. Rapid changes in load, common during maneuvering, stressed components. Engines were often run in pairs or groups, requiring synchronization not only within a single unit but across propulsion systems. In rail service, conditions differed but demands were similar. Locomotives equipped with Deltic engines operated at sustained high speeds over long distances. Vibration transmitted through frames and track imposed additional stress. Maintenance depots had to accommodate engines that could not be serviced casually or outdoors. Specialized lifting equipment was required to remove power units for overhaul. Discipline became the defining survival strategy. Where other engines allowed for gradual degradation, the Deltic tended toward sudden failure if tolerances were exceeded. This encouraged a conservative operating culture. Power was available, but it was used selectively. Schedules were planned with mechanical limits in mind. Over time, crews developed respect rather than affection. The engine was not forgiving, but it was predictable if treated correctly. It rewarded attention with reliability and punished neglect without delay. This relationship shaped daily work. Engineers focused less on innovation and more on preservation. The Deltic did not dominate its environment through force. It persisted through compliance. Those responsible for it learned to align their routines with its requirements, accepting complexity as a constant presence rather than a temporary burden. In this equilibrium, the system functioned. But it left little margin for error, and none for fatigue. As service hours accumulated, the limits of tolerance became clearer. The Deltic's performance depended on precision that time steadily eroded. Wear did not announce itself gradually. It appeared through secondary signs, subtle changes in vibration, rising oil consumption, unexplained temperature drift. These indicators required interpretation, and interpretation depended on attention. Mechanical fatigue emerged first in components under continuous stress. Bearings suffered from the combination of high rotational speed and complex load paths. Gear trains, responsible for synchronizing crankshafts, demanded exact alignment. Even minor deviations could introduce harmonics that propagated through the engine. When this occurred, failure was often abrupt. Documented incidents show that breakdowns were rarely caused by a single catastrophic flaw. More often, they resulted from cumulative stress interacting with delayed maintenance or constrained operating schedules. In naval service, patrol demand sometimes extended engine hours beyond ideal limits. In rail service, timetable pressure reduced opportunities for preventative inspection. When failures occurred, consequences were immediate. A seized bearing or timing fault could disable an engine without warning. At sea, redundancy sometimes prevented total loss of propulsion, but operational capability was reduced. In rail operations, a failed locomotive blocked lines and disrupted service across networks. The human cost was measured less in injury than in strain. Engineers and maintenance crews worked extended hours to keep engines within tolerance. Overhauls were labor-intensive and repetitive. The requirement for precision limited delegation. Experienced personnel became essential, and their absence created vulnerability. Psychological pressure accumulated quietly. Operators were aware that small oversights carried disproportionate consequences. This awareness sharpened attention but also contributed to fatigue. The engine demanded vigilance without providing relief. There were no periods of benign neglect. Accidents, when they occurred, were investigated systematically. Reports emphasized procedural compliance and mechanical limits rather than blame. The pattern was consistent: the engine performed as designed, but the design left narrow margins. When systems surrounding it failed to match that precision, outcomes followed predictably. By the late 1960s and early 1970s, alternative technologies began to mature. Simpler diesel engines improved in power density. Gas turbines became more reliable. The comparative advantage of the Deltic narrowed, while its maintenance burden remained constant. The balance shifted. What had once been accepted as necessary complexity became increasingly difficult to justify. The engine had not failed in concept, but the environment around it had changed. Systems that required less discipline offered greater resilience under modern operating pressures. The Deltic continued to run, but its place within the broader system became provisional rather than central. The withdrawal of the Deltic engine from primary service did not occur through a single decision or announcement. It unfolded incrementally, shaped by maintenance data, cost assessments, and shifting operational priorities. Engines were not condemned as failures. They were reclassified as impractical within a changing system. In naval service, newer propulsion options offered sufficient power with fewer demands. Improved conventional diesels reduced the gap in power-to-weight ratios. Gas turbines, once considered unsuitable for continuous duty, gained reliability and support infrastructure. As vessels were refitted or replaced, Deltic installations were omitted without comment. Existing engines were run to scheduled overhaul limits and then removed from service. On the rail network, the transition was more visible but equally procedural. Locomotives powered by Deltic engines had delivered years of high-speed service. Their performance records were documented and acknowledged. However, their upkeep required specialized facilities and experienced staff, both of which were becoming harder to sustain at scale. By the late 1970s, British Rail began retiring Deltic-powered locomotives in favor of newer classes using simpler engines. These replacements did not exceed the Deltic in raw performance, but they integrated more easily into standardized maintenance regimes. They tolerated variation better. They required fewer interventions. The final withdrawals were handled without ceremony. Locomotives were reassigned, stored, or dismantled according to established procedure. Some engines were preserved for study or display, but most were reduced to components. In naval contexts, decommissioned engines followed similar paths, removed during refits and replaced by systems aligned with contemporary doctrine. There was no sense of loss within official records. The Deltic had fulfilled its role. It had addressed a specific set of constraints at a specific moment in technological development. Once those constraints changed, its relevance diminished. What remained was documentation, maintenance logs, performance data, training manuals, and the experience of those who had operated the engines daily. The transition was not framed as an end, but as an adjustment. The system moved on. The Napier Deltic did not disappear into obscurity. It remained present in archives, preserved locomotives, and technical literature, not as a curiosity but as a reference point. Its significance was never about elegance or ease. It was about the conditions that made such a machine necessary. The engine emerged from a period when constraints shaped ambition. Britain required compact power and accepted complexity as a reasonable cost. The Deltic met those requirements precisely. It did not exceed them, and it did not soften their consequences. Its design assumed disciplined systems and delivered performance only within those bounds. In retrospect, the engine reveals less about mechanical daring than about institutional tolerance. It functioned where maintenance cultures were rigorous and where human systems adapted to machines rather than the reverse. When those conditions shifted, the engine's advantages dissolved without conflict. There is no singular lesson attached to its history. The Deltic was neither a warning nor a triumph. It was a solution bounded by time, technology, and human capacity. Its withdrawal did not mark failure, only the end of a narrow window in which such a solution made sense. What remains is the record of sustained operation under constraint. Engineers who worked with the Deltic did not speak of it emotionally. They described procedures, limits, and outcomes. That restraint reflects the nature of the machine itself. When the engine stopped, there was no silence to mark the moment. Other systems took their place. The rail lines remained. The ships continued to sail. The Deltic passed into history as it had operated, quietly, precisely, and without excess.